Okay, so uh, today we will start a new segment uh, of the syllabus. So, uh, if you recall, I told you that uh, the major part of the syllabus would be mostly about fairness in machine learning, and this would be followed by content governance. So, we have completed these two major parts. Now, there are a few small parts of the syllabus that we would try to wrap up in the rest of the classes that we have left. And one of them is explainability. So, explainability in machine learning. So, no AI ethics course is complete without looking a little bit into the design of explainable machine learning models. So, and that's what we are going to take up in today's lecture, and possibly like if we cannot finish, then we will continue this also tomorrow. So, like this work is one of the like seminal works in explainable in design of explainable machine learning models, and this was published in KDD 2016 by a group of researchers from University of Washington, and the title of the paper goes as "Why Should I Trust You? Explaining the Predictions of Any Classifier." So they assume the machine learning task here to be simple classification, and then like they try to produce uh, explainability or associate explainability with the predictions made by such a classifier. And like I extend my thanks to Marco, like who generously shared the slides with me for this class lecture. Okay. So let us start. So if you look at any like application based on machine learning, you typically tend to see data on one end and application on the other end, and in between there is a pipeline. There is a pipeline of things that are hidden in between these two uh, entities, one of which is the input and the other is which is the desired output. So you have a typically you have a machine learning model which tries to like uh, build an inference system from the data at hand, and then the model learns certain patterns from the data and makes certain predictions and decisions. Okay, so this is roughly the pipeline that any machine learning based application would typically follow. You will have a data set, and then you will have a model that will learn certain patterns from the data, and then based on these learned patterns it will make certain predictions on unknown data. Okay, so that's roughly the thing, and we have been talking about this like almost in every other class. So now this explainability researchers actually pose a trust challenge. So what is the trust challenge? The trust challenge is like you ask a question uh, like is the model that you have designed, is it really working? Okay, so basically what you want to uh, answer, what you want to like get an answer to is that, okay, I am seeing some accuracy values, I am seeing some performance scores, but internally is the model doing what it is ought to do, or what it is meant to do, or what it is designed to do? And like even before you go and try to convince others, it is important that you convince yourself that, like, you know, whatever model you have designed actually is uh, uh, is a realistic uh, uh, like mimicry of of the patterns hidden in the data. Okay, and it is not like some artifact. Okay, so the model is not learning some artifact, but it is learning what it is meant to learn from the data. The patterns that it is meant to learn from the data is what it is learning, not certain artifacts about the data. So the question is like, can we have some principled methods in order to, like, have a convincing answer to this, first to ourselves and then, like, of course, to the others in the wild. Now, so probably like this picture is not new to any one of you. These are like have become the bread and butter for any person working in machine learning. So this is a neural network with certain hidden layers, and you want to ask this question that is this network really doing what it is meant to do? Okay, so as input you give like certain very simple indicators, like for instance running text or some images you give as input, and then it goes through these hidden layers of the neural network, and then it does the prediction. But then what is happening inside the neural network? Like, is it really like doing what you wanted it to do? And this is a question that the authors try to answer in this work. And then, like, following this work, there has been like a huge number of works. So this is one of the very popular works. I think like presently it has more than 8,000 citations. So it's a highly popular work, and many works have followed this work under certain specified settings, under certain very special domains, etc. But then this is one of the pioneering works which we at least need to know in a little bit of detail. So basically, uh, between learning a model and deploying a model in the wild, there should be a phase where you have enough evidence to trust the model. Unless and until you have enough evidence to trust the model, if you deploy the learned model, what happens is that many a times in the wild, the model behaves like the model behavior is not at all as expected. So, if the model was behaving, say, with a 94% accuracy on the training set, and on the known test set with some 90% accuracy. Now, when you deploy the model in the wild, you tend to see that the performance has drastically fallen to somewhere around 55%. Now, why will this happen? Simply because one of the prime reasons that this could happen is that probably what you wanted the model to actually learn was not learned, and the model learned certain artifacts which allowed it to get better accuracy on some known data set, but then this is not working when you are testing the model in the wild, so to say. So the trust part of the model, say for instance, like, can you trust a system like Netflix? So for instance, what kind of trust questions can come here? So maybe Netflix has an algorithm which is recommending certain movies to you. Okay, when you start watching a particular movie, it is recommending a set of other movies to you. Now the question is, why is it recommending those movies, okay, to you? Is there a answer? Is there an answer for this? So if there is a satisfactory answer for this, then probably you can trust the model. Okay, so that's where the explainability thing comes in. So, and like, if you can trust the system, trust a system, and if you know, like, all the nitty-gritties of the model, if you know why certain predictions are made, why certain recommendations are given to you, if you can understand them clearly, and if the model has clear explanations for them, then it is also easier for the user to make better decisions. Okay, and then this further can improve the functioning of the model by taking correct user cues, okay, and feeding it back into the system. Say for instance, like the again take for example the Netflix recommendation of movies. So suppose a bunch of movies are recommended to you, and Netflix also tells you along with the recommendation that okay, you have been recommended this because of your so and so behavior. Now you can look at all of these, and then you can probably guide Netflix back telling that okay, on these three your explanations are correct, but on the other two recommendations that you have given me, your explanations are not correct. So I do not like subscribe to these explanations that you have given. And if you return this feedback to Netflix, then probably that will allow to refine or fine tune the recommendation algorithm, and that will allow the model or the AI system to make better predictions in future. So this is kind of a cycle. So therefore you understand that the reason why a trust model should be present between a model that is built in the lab and a model that is deployed in the wild. Okay. So the question is like, what are the different options to gain trust, say in a machine learning model? Think of some classification task, like what are the ways you can gain trust in a specific ML model? So one way is to design very interpretable models. So these models are uh, typically very promising in their explanations. They have a very strong explanatory power, but then oftentimes it has been found that these are not very accurate. Now, what are the types of models that we are talking about? So these models are typically the feature engineered models. These are not deep learning models, okay? These are not neural networks. So these are like models where you have certain features which are fed into the model, and then like the predictions are made, and then you ask the model as to what are the most important features, most predictive features for this particular task, and the model tells you these are the features, and then you try to get back and reason out. So we had looked into this kind of architectures when we were studying like the early fake news detection, um, uh, uh, like both the cases, like one was the style based as well as the propagation based. In each case we were trying to rank the different features and trying to see like which features are more important and which are less. So these are kind of interpretable models. But then like what about the deep neural models? They are not based on features, right? It's a complete black box. So it's very difficult to uh, like build explanations or generate explanations for such models. But we know that those models are typically more accurate than the feature engineered models. So performance wise, we have observed in like a majority of tasks, the deep learning models actually beat these kind of feature engineered models. So yes, like if you have a feature engineered model like the one you see on the left hand side of the slide, of course it is very easy to give out a reasoning. So what kind of a model is this? What kind of an ML model is this?
Decision.
A decision tree. Okay, a decision tree, a small decision tree, which is like uh, telling you like pinpointing all the reasons for its decisions. Okay, so it's quite explainable, but then at the same, or quite interpretable, but then at the same time many so we have observed that the accuracy is probably not up to the mark. Also, you can have decision trees which are as complex as these. Okay, and here the kind of like decisions that are made at these points, they might not be like uh, uh, they might not be, I would say, so although you know what decisions are made, but these might not be very correct. Okay, the accuracy of the model reduces drastically as the depth of the tree grows higher and higher. Okay, and almost at these points the accuracy is so low that the model predictions are unbelievable. So, and in such cases, like having an interpretation and not having it are kind of same. Okay, so basically, like when you have a small decision tree like this, the model is interpretable because probably the accuracy is still okayish. But then when you have a decision tree which is like having a huge depth, it's very difficult to be assured of the overall accuracy of the system, and therefore like whatever predictions are made, whether they are interpretable or not, the predictions in themselves might not be believable at all because the accuracy falls to such a low value. So, uh, the other way to gain trust is like to believe the accuracy, to blindly believe the, so one is to believe these interpretable features, the other one could be to believe the accuracy. Now, here again there are problems. So, the authors did a very simple experiment. I mean this was done earlier also, but they just did it once again to substantiate their point. So, they have this 20 news groups data set where looking at the mail chain you have to identify whether it's talking about atheism or it's talking about Christianity. So, basically you have to, it's a binary classification task. Given a document or a mail, you have to classify it as belonging to the atheism class or the Christianity class. Okay. So, this model actually when it was trained on this 20 news group subset gave an accuracy of 94%. Okay. And most of the predictions were based on certain clues that the model took up from the email addresses, the names mentioned in the data set. Okay. Now, whenever this model was rerun and tested on a recently built news group data set which has absolutely no overlap with the previous data set, the accuracy went down to 57%. Okay. And this was a realistic experiment that was done. So, you see that just blindly believing on the accuracy value might not be a very prudent thing to do, because as I was telling you earlier also, in the wild the model might like absolutely or severely fail because it might have learned certain artifacts, like here it has learned certain artifacts like email addresses, names, etc. So, rather than learning something which is truly indicative of atheism and Christianity, the model has learned certain artifacts because of sheer large frequency of these artifacts present in like one class of the training set. Okay, so probably like certain types of email addresses or certain types of names were highly frequent in the atheism class. Okay, compared to the Christianity class, and the model picked up this frequent behavior. So, it rote learned this frequent behavior rather than learning the true signals of atheism versus Christianity. And then like when a new data set came in, of course those kind of email addresses and those names were missing, and therefore the model was unable to predict correctly. Okay, so the accuracy fell to 57%. The other way to do it is like launching an A/B testing. So, this is something that companies often do. So, basically they have two variants of the model. Say for instance Facebook is promoting some ad. So, it has one ad variant which is shown to 50% users and another ad variant which is shown to another 50% users. Now, what we observe is that for the first ad variant, the conversion rate is 17% and for the second ad variant the conversion rate is 11%. So basically the conversion rate means the person has clicked on the ad and probably done some transactions through the ad. So that is what is meant by conversion. So what you see is that for the model A, the conversion rate is higher than the model B. Okay. Now, does this prove anything? Can we tell that model A is better than model B? Is model A more trustworthy than model A? From all the intuitions that we have learned so far in this course, can you tell me like whether this conversion rate is a good indicator of the trustworthiness? Or rather, what could be a caveat?
There might be some biases in the demographics targeted.
Excellent. Biases in the demographics. Any other type of bias that I taught you? One is demographic bias, very good. Another type of bias that I have taught you.
Sponsored versus organic.
Nah. So this is something that comes very often in this kind of survey based experiments. Try to recall. Remember selection bias? So what is selection bias? What is selection bias? Exams are knocking at the door, huh?
The sample is not representative of the entire population, right?
No, so there was one more thing. So basically, selection bias or self-selection bias, what might happen that you might have chosen such people who would like who might easily convert. So somehow in the first campaign with this 50% users, there might be many people like who are already like uh, uh, inclined to use those kind of products, and therefore there was a galti in the selection, there was an error in the selection. So the person who launched this study might have like not taken care of such kind of selection biases that could take place. Maybe the first set of people, many of them are Facebook internal users. Okay, so therefore conversion for them is guaranteed, kind of, right? So that's kind of a selection bias, and therefore this renders the A/B testing method also, the outcomes of the A/B testing method also not very trustworthy. So then what? So how do one make a model prediction interpretable, okay, or explainable? So this was what the objective of the paper, okay. Now the question is like, what should an explanation look like? Okay, so this is what the question that the authors start to ask. Suppose you have so this is the same news group data. Okay, so this news group data had one email which had a which looks like this. Okay, so the email looks like this. It has the the uh, sender, the subject, and then some host ID, and then the body. Okay, so this was what was posted by this person. Now tell me, what do you think? So which class should it belong to, atheism or Christianity?
Christianity.
Christianity, right? And when the model was tested, the prediction probabilities were like this. Okay, so it was predicted to be in the class of atheism. Now, why did this massacre happen? Okay, so the question is, why did it happen and how do we fix it? These are the things that the authors tried to answer. Now, as I said, that the model is trying to pick up clues from the training data that is related to atheism and Christianity. And what it does is that, okay, to these two words, Christianity actually gives some confidence to the model uh, about its being, about the posts being related to Christianity. However, you see, it is picking up artifacts like this. Okay, so it is picking up 3 completely useless artifacts. And why is it picking up these artifacts? Because of this reason. So these two words, posting and host, appeared in 21% of the training examples. Okay, uh, so where almost always the class was atheism. Similarly, Kate, for Kate this was 11%. Okay, in 11% of the training examples, if the word Kate appeared, it was, the class was almost always atheism. So you see, the model is doing some rote learning. Okay, it is not learning the actual patterns that it is supposed to learn. It is doing a extreme level of low rote learning, and unless and until you have an explanation chart like this, it is very difficult for you to understand what the model is doing. Okay, so once you have this in place, then probably you can think of devising some mechanism in order to tell the model or feed the model with additional clues that, okay, do not look into these kind of words. Okay, so you have to somehow inform the model, but before even informing the model, you have to know that the model is making mistakes by looking at, by picking up these kind of clues. Okay, so who is going to build this kind of a chart for you? And the authors in this paper actually set this task to build this kind of a chart for you. Yeah, so we cannot trust this model because it does not generalize. Okay, so then they made a, you know, layout of what are the uh, expected properties of a good explanation. Okay, so so some of the properties are what they noted down, and these would be kind of the guidelines for them to design the explainable machine learning model. First thing is that the human should be able to easily interpret. Okay, whatever reasoning is presented, the human should be able to easily interpret. For instance, you see this example, you are able to easily interpret why this error has taken place. Okay, so the explanation that is provided should be easily interpretable. So this, for instance, this kind of a structure is definitely not interpretable. Okay, however, like this one, on the other hand, since it's a small, potentially small data and only a few steps, it's probably much more interpretable. Okay, it should be faithful, it should actually describe, it should not pick up artifacts, it should actually describe that how the model is behaving. Okay, so for instance, suppose these are your data points. Okay, so X is, say, the feature set and Y is the label. So these are your data points, say, for in this space, and suppose this is your learned model. Okay, however, if your explanation is telling that this model is something like this, okay, something like a straight line like this, then this is not a faithful explanation. Okay. So, the faithful explanation should adhere to the behavior of the learned model. So, third, it should be model agnostic. So, whatever ML model you use, you should be able to use the explanator. Okay. The explanator should be agnostic of the model. So, for instance, I should not have I should not need to build one explanator for SVM kind of models. I should not need to build another explanator for CNN models, another explanator for LSTM models. It should be a model agnostic explanator. Okay, that's the third thing. So yeah, for instance, like any messy network like the one shown here, the model, the explanator should be able to explain. Okay, it should not be like afraid of explaining this kind of complex models, quote unquote afraid. So toward this, the authors propose what they call LIME, which stands for Local Interpretable Model Agnostic Explanations. Okay, and this name has become very popular in the machine learning literature since its inception, and then there has been many modifications of LIME and under different scenarios, as I was already telling you. But this still uh, today actually is used in many different applications. Okay, so the key ideas behind the design of LIME are as follows. Uh, so, uh, one is that you try to pick a model class which is interpretable to human. But one of the drawbacks of LIME is that it is very local. So basically, uh, you have a global black box model and you try to make a proxy local model which tries to explain the behavior of the global black box model, but is only locally good. Okay. So it tries to locally approximate the black box model, the global black box model. Suppose you have any ML model, the LIME explanator actually tries to make an approximation of this global black box model by picking up some local signals. Okay, so like some interpretable model could be like uh, drawing a simple line or some decision tree or some sparse features. So line means it could be like using a logistic regression or an SVM kind of a stuff. Okay, so this kind of a interpretable model you define by picking up local clues from the global model and trying to build a locally approximate explanator. We will talk about this in more details. So for instance, suppose this is a point and this is your entire region that you need to classify, okay, using some classifier, and you have some very complex model doing this classification. I want a proxy simple model, okay. I want to build a proxy simple model which has locally good explanations. So for instance, for this particular point, I draw some line which tries to explain why this point has come in the positive class. Okay. So this is locally good with respect to this particular point. Okay. So it's locally faithful. So you try to estimate a locally faithful decision boundary. Okay. And that decision boundary is kind of an explanation for the class that is predicted for that particular data point or for that particular instance of the data. So let's see in a little more details what we are talking about. So the task at hand is you want to design an explanator which tries to explain the predictions of a complex model given an input xi. So, suppose this is an input xi whose input and label is known to you. Okay. So, what do? You sample some random points around xi, that is the first step. Okay. You sample some random points around xi. So, then you use a complex model to predict the labels for each of these additionally chosen samples. So, you have this sample xi, you choose some other samples from around xi, not very far, okay, points around xi, and then you use your very complex model that you have designed to predict the labels for each of these particular samples that you have chosen around the sample xi, around your anchor sample xi. So, let us call this the anchor sample. So, around your anchor sample xi, you have picked up some other sample points, and you are asking your complex predictor to give you predictions for those sample points. Now, you weigh the samples according to their distance to this particular anchor point xi. This is the third step. Now, you learn a new simple model. It could be a logistic regressor, it could be like some simple SVM model, some very simple model, okay, based on these weights, that you have computed. And then you use this simple model to do the explanation. So, the steps are being showed in an animation on the right hand side. Let us see the animation once again. Okay. So, as I said, you will pick up a bunch of points around the point xi, you will predict the labels of those points, then you will weigh the samples based on its distance from xi, and then based on this small set of samples and their labels, you learn a simple model or a simple decision boundary which becomes your explanator, okay, which tells you or which gives you the explanation for the complex model's predictions. This goes on as follows. You pick up some samples, you predict their labels, you weigh them according to their distance, and then you finally construct the decision boundary. So, this is how a simple explanator is designed for a complex model's prediction explanation. So, LIME actually works on both images as well as text. So, let us take an image example and see what the authors did on this. So, let us take this particular example. Okay. So, there are 3 color channels per pixel. Okay, per pixel you have an RGB value, and you input this into a model, but you do not actually input directly all the RGB values. Rather, you break this picture into smaller parts which are called super pixels. Okay, these are contiguous parts, as you see here, like you break the picture into contiguous parts, and each of these contiguous part is fed separately into the model. Okay. So, rather than feeding each and every individual pixel, you feed these super pixels into this kind of a complex say neural network. Okay. So, suppose this is your original image, and the probability that this image actually is of a Labrador is say 0.21. Okay, that is what is your model predicting. So, your neural network model is predicting that the probability that this picture is of a Labrador is 0.21. Now, how do you explain this? How do you explain this particular prediction? Okay. So, what you do is you take these superpixels, and for each of these superpixels you sample a large number of pixels around and a large number of other superpixels around it, exactly the model that I was suggesting. Okay. And from this particular set of like superpixels, say you get a probability that this is a Labrador as 0.92. However, if you select these kind of superfix pixels, you get a probability of 0.001. If you take this one, you get a probability of 0.34. So, basically this is telling you like which parts of the superpixel are actually indicative of the figure representing a Labrador. Okay. So, and you see, I mean, it's easy to understand that this particular uh, uh, set of superpixels are kind of the best explanators for the original image being predicted as a Labrador by the particular complex model. Okay. And so, this is what is exactly being done for each of these individual sets. You do so you can do these perturbation experiments multiple times. You pick up one anchor and you find out like what are the super pixels around it, and based on that you come up with an explanation. You find out another anchor, and from all of this you can finally come up with the set of anchors which actually are most predictive of the original image being that of a Labrador. Okay. And this is kind of an explanation. So, if somebody tells that okay, why is this being predicted as a Labrador by the complex model, you can say these are the superpixels which kind of explains why this kind of a prediction has been made by the neural network model. Okay. So, the question now is, can we really gain any insight from these explanations? So, whatever I have talked so far from this line explanator, can we really gain any insight about the workings of the model? Is this kind of an explanation telling whether my model is trustworthy or not? Is it giving some clue to that? So, is it kind of a litmus test telling me like whether my model is good or trustworthy or not? So, the authors took the Google's inception neural network and tried to uh, pass this particular picture, and the probability that they obtained, okay, that this picture shows that something which is related to a guitar, that probability is 0.32. Okay, and the explanation given by the Lime explanator is this particular area. So, if the model is predicting that it is a guitar, then you see the correct part of the image has been cropped and presented as an explanation. Similarly, if it is like this, then the model predicts that with probability 0.24, this picture is representative of a guitar, and again you get some explanation which are kind of relatable. Okay. Similarly, if it is that of a dog or a Labrador, the model predicts this with probability 0.21, and there the explanation is these two parts of the picture. Okay. So, this explanator that you have designed actually uh, kind of gives you the additional power to understand whether the complex model that you have designed is working properly, is functioning properly or not. Is it taking up or is it picking up the correct signals or not? Okay. And it seems like that the inception model, at least for this particular input picture, is picking up the correct signals based on the explanations that you are obtaining. Okay. However, let us see this example. So, here they train a neural network to predict uh, uh, the distinction between an wolf and a husky. Okay. So they had these examples like the true class is wolf and the predicted class is also wolf, true is husky, predicted is husky. So they only have one particular error. Okay, there is only one particular error where the model makes an erroneous prediction, whether the where the original or the true level is husky and the predicted level is wolf. Now the question is, like, do we trust this model, or how is it that the model is making a distinction between the huskies and the wolves? Any idea how, even without looking at the line explanations? Not very easy, but still. Any wild guesses? Nothing? Oops, I'm sorry. Okay, let me show you the explanations. So when you extract the explanations using LIME, these are the explanations that come up. What is the model learning? What is the model learning to distinguish? Is it distinguishing huskies from wolves?
Sir, it's focusing on the background.
Be a little more specific. You are very correct. Some speciality of the background.
Sir, white or like it's
Yeah,
a
White
color,
matlab kya?
background.
In this case,
color
white
of the back,
matlab? Huh?
Color,
color, color of the
Snow,
background.
Na,
snow is correlated with
snow.
husky.
No, yeah,
Snow. Very good. So that's the thing. The model is actually learning the artifact that if there is snow, then it is, if there is snow, then it is wolf. If there is no snow, then it is husky. So, and until and unless you had this explanator at your disposal, you would never understand what the model is doing. It's all about the snow. It's not at all learning the features of distinguishing huskies from wolves. It's just learning whether the background has snow or not. So that's why only this case where, like, a husky has a background filled with snow, it is predicting it as wolf, because it has learned that anything with the background as snow should be a wolf. So we have actually built a snow detector, okay, rather than a classifier trying to classify huskies from wolves. We have come. So this is what is rote learning that I was telling you, or artifact learning. Okay, so the model starts learning artifacts rather than the realities or the real patterns. Okay. So so did people notice it? So they did a survey with 27 subjects, and they asked this question, two questions, that whether the people trusted the model and whether the people understood the snow inside. Okay, imagine a class like yours, and they threw these two questions. So basically what they saw, that after the example, after the explanation was given, people started distrusting the model more. So along with the line explanations, so initially not many people felt that the model cannot be trusted, but as soon as you presented the explanations, there was a strong feeling that probably whatever is predicted by the model is not correct. However, what was more interesting is that people did not realize that there is this snow detector that has been built out of the model. Okay, so only a very few people actually identified that the model was trying to detect snow rather than a distinction between huskies and wolves. Okay, so but after you showed the explanations, immediately many of them actually correctly identified, okay, so this is a snow detector and not a classifier for huskies versus wolves. So this is how explanations actually helped in order to build trust among people as well as to gain insights about the internal workings of the model. Now, today we have looked into what we do when we have a single instance, and from that single instance how do we generalize and build a predictor. Now sometimes like picking up a single instance does not suffice the cause, and we need to pick up a bunch of such instances and collate them together in order to learn the overall boundary, okay, or overall uh, mm, like explanator. So rather than looking into one single anchor point, if we could find out like a set of very nicely representative anchor points, then it would be probably a more robust explanator that we will be able to construct. So the idea now in the second part uh, of this work, the authors try to select such or come up with an algorithm to select such instances which are the best representatives from the data sample on which they can or based on which they can design their explanator. Okay, so we will see to how they do this in the next class, but the idea is that when you pick such data samples, you want to reduce redundancy, you want to increase diversity of the samples. Okay, so the task now then comes or boils down to selecting those anchor points which are highly representative of the data and are not repeated. Okay, we do not want to repeat same samples. We want to pick a bunch of samples which are representative, which are distinct from each other, and which gives the overall diverse view of the data set. How we are going to do this in order to build an even better explanator, okay, is what we will see in the next lecture. So no longer are we going to pick up uh, some random points around an anchor, but we are going to be very precise in picking up the anchor points so that the overall explanator that we learn is actually covering the entire data sample space very nicely. So how do we do it? We will see in tomorrow's lecture. So stop here.